What's going on, everybody? Welcome to a new video on differential equations. If you're new to the channel, welcome to Lemon's Math, a website where we teach math. And in this video, we'll be discussing about solving homogeneous equations with constant coefficients. But before we talk about that, I want to quickly discuss about solving ODEs in general. So as we know, ODEs are pretty difficult to solve. And for the most part, not a lot of people like them. They're not a big fan of it. And partial differential equations, that's even worse. But part of the reason is way back then, when it comes with solving ODEs, there was really no exact method to solve them. Overall, it was really about guessing. And so if you were a terrible guesser, then you don't know where to start, you don't know what to do. However, as the years went by, mathematicians were able to find general methods for general or specific types of ODEs. And so, lucky for us, we can easily quote unquote guess which method we can use. And so the methods that I have here on this list is pretty much what we're going to be discussing about in the differential equation page. I'm pretty sure there's going to be a little bit more here, but overall it's going to be a characteristic equation, the Cauchy-Euler, series, separation of variables, variation of parameters, and the integrating factor. And for this video in particularly, we're going to focus on the characteristic equation. So that now begs the question, what is the characteristic equation? Well, the characteristic equation is also the auxiliary equation. And it's a method to use for a linear nth order equation with constant coefficient. And to give you a kind of like a little bit more of a visual representation on what it looks, let's do an example. So let's say we are given a second order differential equation, and it's in the form of ax double prime of t plus b of x prime plus c of x, and that's equal to 0. The equations are all respect to t, and a is not equal to 0. And so what we can do is we can guess x, or function x, to be some function such that its derivative is itself. And so there's not a lot of functions in which the derivative is itself, but it should be ringing a bell that there exists such function in which its derivative itself. And if you recall back in Calculus 1, you ran into this little guy known as the exponential function. And so we can let x equal to e to the rt, where r is an arbitrary variable, or not a variable, value. And so once when we take the derivatives, we will get that x prime will be r times e to the rt, and x double prime will be r squared times e to the rt. So what we can do now is we can substitute those functions into the ODE, and we will get this equation down below. And what's so neat about this is because we have this function, or this new equation, we can factor out an e to the rt, and so now we're just left with finding our zeros. And so if you recall in algebra 2, probably, when you first talked about the exponential function, we know for a fact that it will never be equal to 0. And so because we know that e to the rt will never be equal to 0, that puts us in a situation where we can confidently say that the other part, the ar squared plus br plus c, is equal to 0. And this equation here is what it's known as the characteristic equation, or auxiliary equation. And so what we can do is that we can find the roots, in this case it will be r, which will pretty much solve our ODE. In other words, finding the roots of r will find our solution to the ODE. And because this is a second degree polynomial, this will give us 3 cases. So the first case is when all the roots are real. The second one is when we have repeated roots, and the third one is when we have complex roots. And so I'm going to quickly discuss about each case and what that means for our differential equation. And so for the case where we have real roots, if both R1 and R2 are real solutions, then the solution to the ODE will be x of t is equal to C1 times e raised to the R1 times t plus C2 times e raised to the R2 times t, where obviously R1 and R2 are the solutions and C1 and C2 are arbitrary constants. Now for higher order differential equations or higher order characteristic equation, you'll have this general formula. Repeated roots. Well, repeated roots pretty much means that both R1 and R2 are the same, and also that they're real, and that means that our solution to the ODE will be in the form of x of t is equal to C1 e raised to the R1 of t plus x times C2 times e raised to the R2 times t, where again C1 and C2 are arbitrary constants. And so for higher order, it will be x to the t is equal to C1 e to the RT plus x times C2 times e to the RT all the way to x raised to the n minus 1 times c of n e to the RT. And because it is repeated roots, then r is equal to R1 or R2. Last but not least, we have the complex roots scenario. For complex roots, if R1 and R2 are complex solutions such that R is equal to A plus or minus B times I, where B is not equal to 0, then the solution to the ODE is equal to x of t is equal to C1 times E raised to the A times t multiplied by cosine of B of, that's supposed to say a t, not x, plus C2 times e raised to the at times sine b of t. And that is pretty much it for this lecture. We'll be doing some examples that we run across these three cases. And so I'll be seeing you guys in the Blackboard.